Welcome back. We're going to cover the Kelvin temperature scales in this video, and then we'll also get our max performance equations. Now, for our Kelvin temperature scale, remember that is the absolute temperature scale in the metric system. All right, and remember, absolute temperature scale, 0 is the lowest value you can get. That's when all of the motion and everything stops, when you get to 0. Now, the Kelvin temperature scale is also defined so that QC over QH of a reversible cycle, which remember that's like the ideal case, there's no irreversibilities in there, that's going to equal TC over TH. And let's call that equation 1. We'll probably reference that later on. Now, basically what this is saying is two temperatures on that Kelvin scale, which we have right here, they are going to be in the same ratio as the values of the heat transfer that's absorbed and rejected. So remember when we were talking about our cycles, QC or QH, both of those, they were either absorbed or rejected. All right, so this is going to hold true for any reversible cycle when we're using the Kelvin temperature scale. So this will give us another equation to use when we get to our problems. So keep that equation in mind. Now let's look at the max performance equations. For this, first let's look at the power cycle. Remember we had eta was work cycle over QH, and then that could be written as 1 minus QC over QH. Now our eta max, which would be our best possible performance, if we use this equation 1, we could rewrite that as 1 minus TC over TH. And we can say this is the max because notice QC over QH of a reversible cycle, which would be the ideal cycle, is TC over TH. So we just made that substitution. And since we assumed a reversible cycle, gives us the max performance. All right, so this is for the power cycle. And again, note that that would be a reversible power cycle since we made that substitution. And this is also called the Carnot efficiency. We'll talk about the Carnot cycle in a little bit. Alright, so if you have a power cycle, you want to find the maximum possible efficiency, here you go. That's what you use. We're going to do the same thing for the refrigeration and heat pump cycles. For refrigeration, remember we had beta. Beta was QC over work of the cycle, which was equal to QC over QH minus QC. Now using this relationship for the Kelvin temperature scale, we can go ahead and write beta max, which equals TC over TH minus TC. That'll give you your max performance. Now, this is for the refrigeration cycle. And remember, since it's the max, that also means it's got to be reversible, because reversible is the ideal case. That's what you would really want to have if you could have them. Finally, our heat pump, remember that variable was gamma. So we're going to have QH over the work, and that equals QH over QH minus QC. Now using your relationship again from up here, from that equation 1, we can get gamma max. And gamma max will be TH over TH minus TC. All right. So notice essentially we're just replacing our Q terms with the temperatures. All right. This will be for a heat pump And of course it is reversible because it is the max performance. The reversible cycles will always give you your max performance. Next, we'll do some examples using all of these. We'll do that in another video so the video doesn't get too long. I'll see y'all then.